Welcome back, everybody, to another deep dive. You know how we're always using meters to understand what's happening in the world of electronics?
Right.
Well, this time we're going deep on AC measurements,
Oh, cool.
and we'll be focusing on Chapter 15 of our trusty electronics textbook.
Awesome.
Get ready. It's going to be electrifying.
I bet it's going to be a lot more exciting than just volts and amps this time.
You know me so well. We're going beyond just measuring how strong an AC signal is. Yeah, we're going to see how these signals actually behave over time.
Okay.
It's like getting a sneak peek behind the curtain to see the magic of AC in action.
Nice.
And, of course, I've got our electronics expert right here to help us break it all down.
Happy to be here. Chapter 15 dives right into some pretty specialized AC meters.
Okay?
You've probably seen a rectifier-type AC voltmeter.
Rectifier. That does ring a bell, but refresh my memory.
Sure. You see, most basic meters are designed for DC,
Right.
where the current flows steadily in just one direction. But a rectifier is like a special adapter.
Okay.
It uses these things called diodes, which are kind of like one-way gates for electricity.
Ah.
So it takes that back and forth AC current and turns it into a pulsating DC signal,
Ooh.
and then a regular DC meter can actually understand it. Pretty cool, right?
That's really clever. It's like
Mhm.
translating a language so the meter can understand what that AC signal is trying to say.
Exactly.
So we're basically taking that raw AC signal and making it easier for these simpler meters to read. What other tools do we have for AC?
Well, Chapter 15 talks about the thermocouple meter,
Okay.
and it's all about measuring AC power at super high frequencies.
High frequency. So we're talking about way faster than what we use in our homes.
Exactly. Think radio waves, microwaves.
Wow.
They operate at frequencies thousands or even millions of times higher than our standard 60 hertz power lines.
Oh, wow. So our normal rectifier meters wouldn't really work well at those speeds.
Yeah, they would struggle. That's where the thermocouple meter comes in.
Okay.
It uses this neat trick where when AC flows through a resistance, it generates heat.
Right.
And the meter can actually measure that heat and convert it into a reading.
Huh.
And that reading tells us the true RMS value of the current.
So no matter how fast the AC is going, we can still get a good measurement from the heat it produces.
Exactly.
That's really brilliant.
Yeah.
Using heat as a way to measure something as tricky as high-frequency AC.
It is.
It's like a detective using tiny clues to solve a big mystery. So we've got rectifier meters for everyday use, and then thermocouple meters for these really fast signals. Are there any other tricks up our sleeve for measuring AC?
Well, what if we want to figure out the peak-to-peak voltage of a waveform?
Peak to peak.
Yeah, that's the difference between its highest and lowest points.
Okay.
There's a special peak-to-peak AC voltmeter that's made just for that.
So it's not just about the average voltage then.
Right.
It's about understanding the full range of that AC signal. Why is that important?
Well, think about if you're testing amplifiers or circuits where those voltage peaks are really important. If the peaks get cut off or distorted, it messes with the signal.
Right, like when a singer tries to hit a really high note and their voice cracks.
Yeah, exactly. And a peak-to-peak meter gives us that insight into the full range of the signal. Chapter 15 explains how these meters use diodes and capacitors to grab and hold on to those peak values.
Oh, okay.
That's how they make sure the measurement is accurate.
So, again, we're using things like diodes and capacitors to change the AC signal into something we can measure. And that makes me think of another cool gadget, the decibel meter.
Ah, yes, the dB meter. It's not measuring voltage or current directly. It's looking at the power of an AC signal.
Oh.
And it uses something called a logarithmic scale.
Logarithmic scale. Okay, break that down for me.
Well, think of it like this. Decibels take a huge range of power values and squish them down.
Okay.
It's like trying to describe the difference between a whisper and a jet engine, but using smaller numbers.
Right.
So each time you go up 3 dB, the power doubles. And a 10 dB increase means the power is 10 times greater.
Oh, I see. So it's not just measuring how much power there is, but it puts it in a context that makes more sense. Why do we use decibels so much in electronics?
It's all about convenience and how we hear things.
Okay.
Our ears actually respond to sound in a kind of logarithmic way, too.
What?
So the dB scale matches up with how we naturally hear changes in loudness.
Right.
Plus, in electronics, we often deal with really big differences in power. Decibels just make those differences easier to handle.
That's fascinating. It's like we've made a measurement system that copies how our own senses work.
Yeah.
So a dB meter is a great way to understand how strong an AC signal is, whether it's for audio, radio waves, or even power levels in a circuit.
Exactly. And Chapter 15 gets into how dB meters use amplifiers and rectifier circuits to turn those power levels into decibel readings we can understand.
It's amazing how we can take this invisible thing, AC, and
Yeah.
figure out ways to measure it, analyze it, and really grasp how it works. We've got meters for general voltage and current, specialized ones for high frequencies, and those peak values, and now the dB meter to help us understand power levels in a way that's meaningful. It's like we're building a whole language for talking to the world of AC.
Yeah, it really is amazing. It's like a mix of how electricity works and how clever we are at making tools to measure it.
Right.
Speaking of tools, Chapter 15 brings up this pretty cool one called a distortion analyzer.
Distortion analyzer. Sounds kind of serious.
It is. It's all about how pure a signal is.
Ah.
Remember those perfect sine waves we always see in textbooks?
Yeah.
Well, in real life, AC signals can get messy.
Okay.
They pick up extra frequencies or harmonics, which kind of warp the original wave.
Ah, so it's like listening to a song with static or crackling. You can still hear the music, but the quality is bad.
Yeah, exactly. And in a lot of electronics, distortion can be a big problem.
I can imagine.
Like in audio equipment, you want those clear high notes and deep bass without any fuzziness.
Right.
Or in communication systems where distortion can garble messages.
Yeah, that makes sense. So distortion is basically the enemy of a clean signal. But how does this analyzer actually work? Does it have some kind of sensor that detects bad waveforms?
Not exactly a sensor, but it has a neat way of finding and measuring the distortion.
Okay.
It's like this. Imagine you could filter out the perfect main frequency of an AC signal.
Yeah.
What you'd have left over is the distortion part.
So it separates the noise from the good music so you can see how bad the distortion is. What kind of information does it give you?
Well, a distortion analyzer tells you what percentage of the signal is distorted,
Okay.
so you know how pure it is.
Right.
It can even break down the distortion into those harmonic parts,
Oh.
showing you which frequencies are causing the problem.
Huh.
This info is super helpful for fixing and tweaking circuits to get rid of that unwanted distortion.
So it's like a doctor for our AC signals, keeping them healthy and sounding good.
Exactly.
So we've covered meters for basic measurements, specialized meters for different things, and now an analyzer to check signal quality. What else is there for measuring AC?
Chapter 15 talks about this really interesting thing called spectrum analysis.
Spectrum analysis.
Yeah, imagine being able to see all the frequencies inside an AC signal.
Wow.
Not just the main one, but all those little harmonics and other frequencies hiding in there.
That's pretty wild. What kind of tool lets us do that?
It's called a spectrum analyzer. It's a pretty amazing piece of engineering.
Okay.
It basically shows you a picture of all the frequencies in a signal and how strong each one is.
So we're not just measuring one frequency or voltage anymore. We're looking at the whole frequency fingerprint of the signal. Why is that so important?
Well, think about if you're trying to fix interference in a communication system.
Yeah.
You need to know which frequencies are causing the trouble.
Right.
Or if you're building a filter circuit to get rid of noise, a spectrum analyzer shows you exactly which frequencies to target.
It's like having X-ray vision for frequencies. You can see hidden signals, figure out where interference is coming from, and even understand complex waveforms that a normal meter wouldn't be able to handle.
You got it. And Chapter 15 explains how spectrum analyzers use some really clever techniques with frequency sweeping and filtering to make those detailed pictures of the frequencies.
It's amazing how much we can learn about AC signals just by breaking them down like this. It's not just about reading numbers, it's about understanding how these signals work and how they shape the technology all around us. It's really incredible how much information we can pull out of these AC signals by breaking them down.
Yeah.
But all this talk of analyzing makes me wonder, what if when we actually want to create AC signals?
Oh,
Are there tools for that too?
Absolutely. Chapter 15 introduces us to something called a function generator.
Okay.
It's like having a whole bunch of tools for creating different AC waveforms.
So instead of just measuring what's already there, we can make our own custom signals. What kind of waveforms can it create?
Oh, all sorts. Sine waves, square waves, triangle waves, even pulses and ramps. The function generator lets you control the frequency, the amplitude,
Right.
and even the duty cycle, which is like how long a pulse stays on compared to off.
It's like a musical instrument for AC.
Exactly.
You could compose a whole electrical symphony with all those different waveforms. But why would we need such precise control over those signals?
Well, think about testing a circuit to see how it responds to a specific frequency.
Hmm.
Or maybe you're calibrating a piece of equipment that needs really accurate timing signal.
Oh, I see.
That's where a function generator really comes in handy.
It's like having a tiny power station in your lab.
Yeah.
You can dial in the exact type of AC you need.
Yeah.
This is amazing.
And Chapter 15 goes deep on how these function generators work, from making those basic waveforms to shaping and changing them to make all sorts of signals.
It's incredible how much we've covered, from simple AC measurements to this advanced analysis and even creating custom waveforms.
Mm.
It's a whole toolkit for understanding and working with this fundamental force of electricity.
We really did go on quite a journey.
We did. We started with that basic question, how do we measure AC?
Mhm.
But it turned out the answer is anything but simple,
Yeah.
and has led us to this deeper understanding of how we can use AC to create and build new technologies.
Exactly. This is just the beginning, though. The world of AC is vast and always changing.
Right.
So keep exploring, keep asking questions, and keep that curiosity alive.
Absolutely. Thanks for joining us on this incredible journey through the world of AC measurement.
It was my pleasure.
And until next time, stay
Yeah.
curious.